Welcome to Did You Know? The ESCO HVAC Show. We will see you in about 45 seconds or so. Make sure that you are subscribing to our channels, our LinkedIn, YouTube, Facebook. Turn on notifications, and we are very excited to be here with you. It's almost time, about 30 more seconds. Make sure to grab your notebook and pen so you can jot down notes along the way, because at the end of the show, you could have an opportunity to ask our guests questions so we can dive a little deeper into these topics. And here we go. Welcome to Did You Know? The ESCO HVAC Show. Well, hello. Thank you all for joining us. We are really excited to start talking about things that are happening in our industry. Today, we're spending time with Darren Kramer from Fujitsu. Darren, how are you, my friend?
Doing very well. Thank you.
So we spent time talking about changes in our industry, especially from the decarbonization perspective and new equipment, new refrigerants that we're working with. I actually just came back from the Eastern Energy Expo myself, which is primarily a heating oil industry, but they're even talking about new trends and technologies. And there were classes on ductless mini splits and VRV, VRF systems as well. So the entire industry is preparing for new technologies. Now, inverter technology is not really new to the industry, is it, Darren?
No, it's not.
And the big difference is it has a variety of components that we may not be used to working with our traditional single stage and two stage equipment. So as we move into our inverter technology, it's critical that we have a better understanding of the fundamentals of operation so we can see how they work, so that we can maneuver a couple of our practices on installation that we may not have been doing 100% correct previously, that is going to be very important going forward. And then when we get into the service and the diagnostic side, we actually have a lot of tools in our ductless and our inverter systems that we didn't have at our disposal before. So this is going to be a fantastic course. I thank you so much for joining us today, Darren. And tell us a little bit about how you got into the industry before we dive deep into this conversation.
That's always the story. Well, I started off, I wanted to be something different than an HVAC guy. I'll just say that first off.
Well, yeah.
Whenever I had a chance to go to work for my dad, he had an air conditioning company he just started. And so I decided to join him, and that's where that career got started.
The bug.
Yeah.
Yeah, fantastic.
I've been doing this about 37 years.
And what is your role right now? What do you do at Fujitsu?
I'm the National Training Facilities Manager. So I develop curriculum for our residential side, and I also do train the trainer for all of the distributor instructors. So I get them up to speed and help them to learn the material.
Awesome. So when we're talking about a mini split system, how do they function? Most people learn sequence of operation for gas-fired appliances and sequence of operation for, basic refrigeration circuits. What about our mini split systems? How do they actually function?
Well, we're going to talk about that today. They are totally different than what everyone's accustomed to with traditional heat pumps.
Yes.
So there is a big difference. We'll talk about the differences between them. We'll discuss some of the components, how they function and how they work, and then how the whole system itself works together, both inside and outside, to make it different and considerably more energy efficient.
Yeah, definitely. Okay, well, let's get rolling.
All right, let's go ahead and start. So we're going to talk about not just the inside, but quite a bit of the outside components are going to be discussed as well. And we're going to see how all of these are working together to make the system work. And we're going to find out why it modulates and does the things that it does.
Yeah.
So one of the differences in rotary compressors is that they're very, very efficient. There's some advantages of them being a DC three-phase inverter that modulates. It's looking at the capacity based upon different load conditions that are going on inside and outside. We'll talk about some of the components that talk back to the system and let it know how to do that.
Yeah, the communication side.
That's right. And we'll look at how it ramps from lower speeds to higher speeds. And I know there's a lot of guys that when they first saw an outdoor inverter running, they thought, well, there's got to be something wrong with the fan motor. It's not going very fast.
Right.
So we'll look at that. And it's interesting how, because of its design, especially when you're looking at getting oil return back to the system.
Right. Very important.
Yeah, there's a lot of guys say, well, how can you pipe something out 164 feet or 230 feet? I can't do that with a traditional system. And it has to do with the speed that the rotary compressor can run and ramp up to get the oil back to the system. So
yeah, a lot higher RPMs of what people are traditionally used to, especially
yeah,
with recips and scrolls.
yes, that's correct. So when we start looking at the operation on the frequency range, this is an example of just the models. You can see we've got an 18, 24, and a 30. And both in cooling and heating, now these RPSs, or revolutions per second, of the compressor vary from model to model.
Sure.
But you see how they have a very low minimum and a higher maximum. And that all depends upon the operating conditions currently. What's the temperature outside? Is it mild? Is it a mild temperature inside? Well, if it is, you can see that we're probably on a mild day not ever going to get to any of these high RPSs that you see for a max.
Yeah, absolutely.
So that's different when you compare that to like a traditional system that is just,
single RPM speed.
It doesn't know what's going on. It's kind of like, it hasn't, grown up yet.
Yeah, exactly. Yeah, a lot of people don't even realize, like, what two-stage system, most of our traditional two-stage systems, they don't change RPMs. They just bypass refrigerant to change the load. So the motor of the compressor is just running at a steady state. It's never doing variable capacity.
That's correct. And so when we start looking at things, not just the compressor, but now the outdoor fan motor, depending on the model, again, will depend upon what RPM it's designed to run at.
Right.
And so what's happening is it's looking at the temperature of the heat exchanger. Now, there's a lot of things that could impact that. If it was a dirty heat exchanger, then the system would basically say, your subcooling's off. I need to speed up the fan to try to get more air across that heat exchanger. So that's why it's important to have a good, clean outdoor coil all the time.
Critical on these systems.
Yeah, and as you look at the different models here, you can see that they're designed to run at varying RPM. So depending on where the system is at, both temperature-wise outside and inside, depending on what the load is, will depend upon how far up the modulation that it's going to go. So it's nice to understand, what makes these fan motors increase in speed along with the compressor.
Now, I noticed with the compressor that was going between, especially on that smaller unit, from 20 RPS up to 100 RPS. So we're looking at a unit that can go from 20% capacity up to 100% capacity, approximately?
Yeah, somewhere in that range.
What are we seeing with the outdoor fan motors? How much range, how much capability of movement do they have?
Well, they have quite a bit. I mean, this is just an example of where the RPM could be on, like in the cooling, from 200 up to 780.
Yeah.
So again, if we're on a mild day, if you wake up in the morning and it's 80 degrees outside and your system just needs to start up, everything's going to be modulating slow. You probably won't even get to half speed.
Oh, wow. Okay, sure.
On a mild day. So again, it's still looking at the temperature outside and it's looking at the temperature inside. So as the outdoor fan's running, if the temperature goes up outside, then that's going to change how the outdoor unit's getting rid of the heat that's hitting that heat exchanger. So it's naturally going to pick up some heat from the outside temperature going up. The system's going to see that, and then it's going to make a change to make that fan go a little bit faster to get rid of the heat.
Okay.
So when we're talking about the outdoor fan motors, a lot of times guys are like, well, what's the voltage of it? Well,
right.
This is an example of two different voltage readings that has to go to the outdoor fan motor. So if you were to check on the red and the black wire, you would see anything from 260 to 400 volts DC on this particular model. Now,
right.
Voltage can change depending on the model and the size of the unit. But then if a technician went out, he would also have to check the white and the black wire, and he'd have to have something between 13.5 to 16.5 volts. If he got both of those voltages, then that motor should be running.
So we're basically incoming line voltage on our high voltage DC and then our control voltage on our low volt DC?
That's correct. So that can be checked by actually taking a reading on the board outside. So if
Sure.
again, you're going to need some sharp test leads,
Yeah, I'd got to have those micro leads.
and you better be very careful whenever you're taking that reading,
Right.
especially taking it live. So that's the basics of the voltage we're looking at for a motor. And again, it's just a matter of testing the correct pins. And you can see that the pin, for like test one, you're looking at the red and the black wire. So
Okay.
easy enough to check, and then you check the black and the white for test two. Now, if you didn't have those readings, then that wouldn't mean that the fan motor is bad outside. That means you may have a problem in the board itself.
Sure. Now, would that be a time to do you disconnect the plugs to check voltage at all?
Not generally.
Right.
Most of the guys would probably check these right at the board itself.
Sure. Make sure that we're feeding from the board and then getting to the motor.
Yeah, because it's up top and a lot easier to get to.
Yeah, absolutely.
And if you look at the picture of the upper right, you can see where it says DC fan motor, and it's got a little white imprint on it, so you know
Oh, yeah.
exactly which connector you're looking at.
Okay. Fantastic.
So the big question always comes in,
Mm.
well, how does it work? So we're going to look at some of the components that are part of this process. Now, this is where the power first comes in. So this is the power filter board that you see in the outdoor unit. So we have line voltage that's coming from our circuit breaker and coming into the board. And depending on the model of the outdoor unit, it could be a
Right.
15 volt or it could be a 230 volt.
Yep.
So that power is going to come in. Then that power filter board is going to send voltage over to the diode bridge. And then once it does that, then that's where you're going to have that conversion from AC to DC voltage. So once you start understanding where the power starts at and where it goes to next, you start to understand that there is a pattern and a process of routing the power through various components to get to the end source, whether that be a fan motor or whether that's the compressor or EEVs or anything else. So this is where it all starts, and then it starts to move over to the main board outside.
So it's a flow. It actually is a sequence of operation. A lot of people say that there's not really a sequence of operation for a inverter system because it's just inputs and outputs. But it really is if you understand where do we begin and how do we make something happen. Yeah, we have inputs and outputs, but there is definitely a flow throughout the entire circuit.
Yeah, everything is very dependent upon each other. So it's possible, sometimes you'll hear a technician might say, "Well, I had to change several components out. If something went wrong or something went bad with one of the components." That's because they're tied together.
Right.
So one could short out and cause
Affect the other.
yeah, affect the other. So they're part of this big family. Now, we talked about going from the diode into the diode bridge. Well, the diode bridge is going to convert the AC to DC. So you see the little circle and you see all the nice little paste,
Yeah.
heat sink paste. If that screw's not down snug and tight, especially if you were to replace that, you wouldn't be but probably 30 seconds and you let the smoke out of the board.
Absolutely. I've encountered that many times out in the field, and that's very important to understand that we're converting heat in this process, and that heat must be dissipated away from the control board. And so the heat transfer between our sinks and right on these tabs is absolutely critical. So if we are doing a board replacement, we need to remove the grease that is there, supply with fresh grease, ample amount that it actually makes full contact with the entire plate, and that our screws, all of the screws, are put back if you have multiple screws, and that they're torqued down properly.
That's correct. And if you look at the picture toward the bottom, you can see where the air is coming through from the blade. Well, right above that, you can see some spider webs.
Right.
So it's not a bad idea, at least maybe annually to, blow that out and make sure that you don't have a lot of dust that's accumulating up underneath that heat sink, because you could get some things over time that could act as an insulator to it.
I had that conversation just this weekend about doing service on these inverter systems. If you're only cleaning the surface of the coil and not looking to see that if the heat sinks are clean on the inverter dissipation, then you're not doing a complete service on that piece of equipment.
That's correct. All right, so let's talk about the IPM. This is a term that we use. It's called the inverter power module.
Right.
Now, this is the little board. Now, I know what this is because it's a little smaller board, so I know that goes to a single headed system. So it's just
Okay.
it's not a multi-zone. If it was a multi-zone, then you would have a power inverter module that would be built into a big, large board.
All in one component?
So this is for the smaller single zone systems.
Okay.
And this is what controls the operating speed of the compressor. So it's
Oh,
changing and varying the frequency of the power through high speed switching.
okay.
So it can speed it up and it can slow it back down depending upon what's going on with the system at the time. So it too has a little you know diode on it that gets very hot. It has to be heat sink pasted down as well. But this is the little brains of running that compressor and telling it at what speed it's supposed to run at a given time.
I've also seen in some of my installation manuals the IGBT, integrated bipolar gate transistor. Is this the same design, same function?
Yes.
Okay.
All right. Now we're going to talk about the active filter module. And now this is a component that is pretty important. As you get into the really super high SEER rated equipment,
Uh-huh.
you won't necessarily see this module on our unit, but what it does is it's filtering out the harmonics that's produced by the DC compressor.
Oh, okay.
So if you remember back when you were a kid, if you're older like I am, you probably remember the times when you use a hair dryer and you're watching the black and white TV and you see it.
Absolutely.
Well, that was what was causing it. There was some harmonics coming back
Okay.
on the house. So this helps that harmonics to not feed back on the house, which is caused by a DC compressor.
Okay. Very important part.
So it also does other things like modifies the voltage output. And we're also looking to improve the power factor. The better the power factor, the more efficient and clean the signal is going to be going to the other components.
Okay.
So that's important that you have a device like that to do that. Now, this also gets very hot. If you were to look on the back side of this active filter module,
Right.
you would see a metal plate. Well, that metal plate on the back side is where you put all of your heat sink paste.
Oh, okay.
And then the two holes you see there would actually screw that down to the heat sink aluminum itself.
So the entire module is part of your heat dissipation.
Right.
Nice.
And so what we're doing is we're modifying the input current, and we're really attempting to get a 100% power factor. Now, we're not quite going to get that, but the better we do, then the cleaner the signal and the better the system's going to work, the more efficient it's going to operate.
Sure. Absolutely.
So it's an interesting little component. Out of all the, a lot of times the guys will say, well, what's the most common thing that could go out on one? Well,
Right.
active filter module could. And one of the things that can take components out, a lot of times technicians don't understand this, but by the time you get out to the house and you're like, well, this it's gone bad, and you checked it and everything. Yeah, I need to go get another one. You come back and put it on, it works great. And then maybe a week later, a month later, it goes out again. Well, a lot of times technicians don't check the incoming voltage to the equipment.
Oh, okay. Sure.
So if the power company is giving you higher voltage than the system is supposed to have, it could take out components like this because it's generating more heat within the module itself. So they don't know that that's what's causing it, but that is a very high possibility that you could be getting some higher voltage.
Now, when I was out doing education at the distributor level, I always encouraged voltage monitoring devices for my inverters, like the ICM, like the 493s, and units that actually help modulate the incoming voltage. Is that recommended by a manufacturer or not? I've always wondered on that debate.
Oh, we would love it if everybody put those on.
Okay, I always thought so because I encouraged it for every inverter. I've actually had power areas like at the very end of a line on rural areas that had very high voltage drops that kicked out very regularly on voltage control. And using a power monitor before our power supply to the unit, so disconnect to voltage monitor to our inverter outdoor unit, would eliminate those problems. So I personally recommend them for every inverter installation.
Yeah, there's a lot of guys go, well, why don't you just build that in? Well, if we did, it'd make the equipment cost more.
Right.
And there's guys that'll be like, well, I don't really need that here. But if you put them on, then the chance of a homeowner having a problem is considerably less, and it protects the equipment. And let's face it, if the component goes out, we're not going to know why the component went out. We didn't. we didn't know there was a lightning strike or there was a power surge. All we know is someone's bringing the part back to the distributor and saying, "Hey, I need another one."
Right.
Well,
This is bad.
that costs us money, as a manufacturer, but we don't know why it went out.
Yeah, exactly.
And the homeowner's like, well, they don't know why it went out, and they end up having to pay labor. So, you know, I know there's contractors that are doing what you're saying more often. They're just building it into the price.
Yeah, it's good insurance.
And there was one, that was telling us about a high school they had, and it was up on top of a big hill, and it was known for getting lightning strikes up in that area. So
Sure.
they put 27 of these on.
Yep.
Talking about it hit the school finally. When it did, it knocked out all the units. But when they took those off and they turned the power back on, the units ran fine. It damaged those devices,
Yeah, absolutely.
but that's it's supposed to save it.
Yeah, that's an insurance. Absolutely. I had one particular unit that would smoke a main control board every couple of months after installation. So the product itself was starting to get a bad reputation. When I went out and did the site visit for it, did analysis on what we were actually seeing in the field, we were seeing some floating voltages. We had a new power distribution center put in half a block down, so we had some floating voltages while I was on site. So after installing a voltage monitor on the system, all of our fluctuations disappeared, and none of my boards were having failure issues after that. So
yeah. So on my
very
desk
important.
right now,
Yeah.
I have one of these. I've got to put it on my mini split.
Yeah.
I just put a system on my house, so I've got to install one as well.
Yeah.
So
Absolutely.
I just thought I'd just pop that up.
Yeah, highly encouraged.
Yeah, I've got one. It's getting ready to go on mine too.
Yeah, exactly. And everyone that's joining us, let us know where you're chiming in from. We appreciate everyone being here. If you have any questions along the way, let us know. Just let it hop there in the chat box and give us some input, and we'll think about it. If we don't have it on this particular slide, we'll get to it later. And then at the end, we'll have a chance to come back as well. But we definitely want to know where you're calling in from, and what of this is very important and what it's going to be doing to help you in your success.
All right, so let's talk about the EEV. A very simple device, but its ability to control the flow of liquid is tremendous. It's so much different than just a standard TXV. So this is powered by 12 volts DC, and it's just a pulse-driven needle valve that goes up and down. It's got a magnetic coil, and we'll show you how it all kind of clips together in just a minute.
Sure.
So how does it work? Well, it has a software algorithm that controls the opening and closing of it. So depending upon what the load conditions are, will depend upon what that EEV is going to do. Now, the EEV is not going to make any changes until the system tells the compressor and the fan motor it's time to speed up a little bit. Once it does that, if it says, hey, we need more load, then it knows exactly through the software algorithm to tell that EEV, you need to open up to this level, this many steps, and then stop.
Okay. Yeah, absolutely.
So, when you think about it, it's kind of like a kitchen faucet. If you barely crack the kitchen faucet, what do you get? A little bit of volume of water. What if you open it midway? You get more volume of water. Open up all the way, you're getting all the water it can give you. Well, that EEV is just controlling how much liquid is going to flow from the outdoor unit to that indoor.
Now, one question I've actually always had for myself, I've never had the opportunity to ask a manufacturer. Are we able to go from 0 all the way through 100? Can we be completely closed and be 100% open on our EEV flow valve?
It's doubtful that you would be fully open to the full steps that are there. From what I've seen in our literature is that it's designed, different models will open to a certain number. Maybe it's 420, maybe it's 460. It'll never hit the 500.
Okay.
It's designed to open to whatever the engineers have decided.
Okay, that's good. That makes more sense now, because I kept seeing different stepping, and I thought, surely there's not that many different valves out there.
Yeah, so it will go down and close to stop the refrigerant from flowing. You wouldn't want to have a little bit of refrigerant just flowing without the fan running. And you'll see a little bit later, you're going to see a little diagram of how that works.
Okay.
Cool. So here we have an example, since we're talking about the pulse range. This goes right into it. So on an 1824 or 36 model of this particular unit, you can see that in cooling mode, we have a pulse range between 50 to 480. So it's going to pulse to at least 50 as the
Mm-hmm.
minimum that it could flow through. Now, that range is up to 480. Some other ones could have a little bit higher range, but in heating mode, so you can see it's different than it would be for cooling mode.
Yeah, definitely.
So what's happening again is we're looking at what's going on with the compressor frequency, what's happening with the discharge temperature sensor, and what's going on with the outdoor temperature sensor. That is information that tells us exactly where we need to go. Now, if we're talking about our initialization of the expansion valve, you can see here it says that 1,000 pulses of are input to the closing direction. So it will reinitialize itself and reset
On
itself,
startup.
and then yeah.
Okay.
So that's just part of how engineering works with how it starts up in different modes, and then what ranges they run
Okay.
through. So this little coil you see up here, we're going to go ahead and we're going to push it down. So this coil can be lifted up and off. You can see where it would clip onto the refrigerant line. So let's just do our animation there.
Nice.
Oh. So the main thing is do you have it clipped on and is it nice and snug? If that was to come off in shipping or something unusual happened and it lifted off, then you wouldn't hear that tick 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 sound when you first started the system up. So if something like that ever did happen, you just want to make sure that it is clipped and snug on that.
Yeah, and I've actually seen that out in the field, not on your brand, but I have seen that before where in shipping that has not been completely seated down. I've even seen some where we're just partially, where like the tines were pushing onto the side of the tubing. So it was, a 16th of an inch from being seated, and therefore it wouldn't open and close properly. So very important just to make sure that it is snapped down into place and seated correctly.
We have no way to control truck
No,
drivers.
absolutely not.
All right, so let's talk about our thermistors. Now, this is the indoor thermistors you're looking at right here. So in the upper right, the refrigerant temperature, it's got that little copper barrel. It actually fits down into a little bitty well that checks that temperature coming in. Then we have the ambient thermistors. So the system is looking at these resistors.
Okay.
Now, these are the king of how the system
Yeah,
is
aren't they
going
though?
to. If you don't have all these thermistors, and you could easily have up to 9 of these in a
That's right.
system. So if you don't have them, the system would not know where you're at and what you need. It would just be like, well, I don't know. I just have to go full out. So it's looking at a change of resistance with a change in temperature. So as the temperature goes up, resistance is going to go down, and then vice versa. So as that temperature is changing, then what's going to happen is we're going to get a small output voltage that's going to be provided to the PC board. Now, this 5 volts DC is going to come out of the board, and it's going to go into the thermistor. It's going to route through the thermistor and back out. And because there is resistance in the thermistor, there's going to be a drop in voltage. So it's that reduced voltage that's coming out of these thermistors that's actually the input information back to the board. It's not like the thermistor says, "Oh, I'm 75 degrees" or "I'm
Right.
whatever." It's looking for a drop in the voltage going through that, and whenever that voltage comes back to the input board, that information is then going to be sent to the outdoor unit, and it's going to say, "Here's what's happening inside." And the outdoor unit says, "Oh, I see your voltage is changing. It looks like it's getting warm in there," and then it starts to tell the system it's time to modulate.
Sure. Absolutely.
So it's a very interesting correlation between the indoor thermistors and the outdoor thermistors, all both sending information to the outdoor board and telling it, "Here's where we're at," and then it makes the decision on what it's going to
Now,
do.
in your service manuals, do you provide the chart that shows what those output voltages are based on temperature?
Yes,
So,
and so if somebody wanted to go in and actually, check a thermistor to see if it's within the ohm range it's supposed to
right.
be, you just need to know what the temperature is at that thermistor. So, and typically when you get that number, you're going to be 10% high or low of that
Yeah,
number.
absolutely.
You're good. If you get outside of that range, then you've got a bad thermistor.
Okay, 10% rule of thumb. Good to know.
So that is available. Now we've got the outdoor ambient thermistor. Well, everyone's got, man, you guys got so many thermistors.
Right. What all are we reading?
Well, that's how the system knows exactly how much capacity it's going to run at. If you take a single speed, heat pump, it doesn't know anything. It just knows that the thermostat inside said, you set me at 75 and the temperature went to 77 or 78. I need to turn on. It has no idea what's going on outside. So that's why people are using so much more energy with traditional heat pumps. And this is what makes these so much more energy efficient, because why should you use more energy than you need? Or why do you need any more capacity than what you need under the current conditions you're under? You don't need full.
Absolutely. Well, even think about things like defrost cycles. Look at a traditional heat pump that used to use a snap disc defrost, where we had a wide range of control that was only reading a refrigerant line temperature. Well, now we can utilize things like outdoor ambient thermistors to know what the temperature is outside in comparison to the temperature it's on my coil.
Oh, if we were to talk about that,
that's a whole class, isn't it? We might have to go back to that one.
I could talk 20 to 30 minutes on how we utilize our 6 defrost sides of our system.
We got to come back to that one day.
So pretty interesting. All right, now we have another thermistor. We've got the compressor discharge thermistor. It protects the compressor if the high side was to get too high. And it will also generate an error code. So if there was a problem, whether or not that's a outdoor fan motor failure, or the bearings went out or starting to go out and was turning too slow, or let's just say that the outdoor heat exchanger was just all stopped up and dirty and needed to be cleaned, well, that could impact this compressor discharge thermistor. So we don't want the compressor to be damaged.
Right. It's the most important part.
And so the way this works on this particular model is you'll see that it says the protection stop is when the discharge temperature is greater than 230 degrees Fahrenheit.
Okay.
Or 110 degrees Celsius. And it has to be generated 2 times within 24 hours. If it counts that within 24 hours, then it's going to throw an error code up and it's going to shut the system down and give you the flash.
It's going to lock out and go, hey, we're running too hot. We're not going to lose this compressor. Come take a look at me.
And that's so much different than a conventional system.
Where I run till I die.
Yeah, it just runs until the compressor just strokes out.
That's the beauty of our inverters. People don't always understand how self-controlling they are. They have so many safety, apparatuses built in, looking at these potential problems and giving you the opportunity to come take a look at them before they become catastrophic.
That's correct. All right, so we get into the heat sink thermistor. We got another one. So what's this one do? Well, it's monitoring the temperature of that aluminum heat sink that it's tied to. So, if the outdoor fan motor continues to move air across that heat sink, then the diode bridge is going to be happy. If not, then what happens is this thermistor is designed to open up before you lose your diode bridge. Because that thermistor is a whole lot less expensive than that board.
Very cool. Yeah, so we think about some of the conditions down the road. What if we're, coastal and we have, oxidation that dries out our grease? What if we're in direct sunlight? We have oxidation, we have heat that dries out our grease. We don't see it very often, but we know that if we lose that conductivity of heat, that we're going to cause some problems with our control board.
Very true. Now we get into the heat exchanger out temperature thermistor. So this is looking at the subcooling that's happening through the heat exchanger. Now, if that number is coming back different, what could happen with this one is if it senses a temperature that's not favorable, and if the algorithm cannot keep the subcooling in the range it's in, then it's going to send the information back to the outdoor board, and the board's going to say speed up that outdoor fan motor.
Okay.
So it's still trying to maintain the subcooling, and at the same time, it's trying to get enough heat. So if your outdoor coil gets dirty, and it just keeps getting dirty, and grass gets in it, and the dog lays around it, and eventually, you could have another thermistor shut the system down. But we're trying to see what the subcooling number is and see if we're still matching up to our range that the system's programmed to run within on subcooling.
So would you say that the heat exchanger thermistor is the primary control for the outdoor fan motor?
Now, I'd say it's
It's all a
all of
piece of it. Okay.
it. Now, as far as the outdoor fan motor is concerned, uh, again, it's going to speed up depending upon what's happening to the outdoor temperature.
Right.
So if the outdoor temperature keeps climbing and you go to 100 degrees outside, well, you know that the outdoor ambient thermistor is going
It's
to
already give
say
its input.
that one's already, being one of the keys. The second one here is this one, because this one's going to determine whether or not we're staying within the subcooling range.
Exactly.
So the system needs to be monitoring subcooling. At the same time, for capacity reasons, we need to know what the outdoor ambient is and what the indoor temperature
Yeah,
is.
absolutely.
So that's how we increase capacity. But then now controlling subcooling is dependent upon whether we have a clean coil and we have enough air moving across the system to stay within there.
Okay.
Now, when we get into the two-way thermistor, this is in a multi-zone system. You can see we've got 5 different um, EEVs in the outdoor unit. So this is a 5-zone system.
Multi-port.
It's monitoring the suction line temperature, and again, it's acting as a protection as well. It can also provide an error code if it needed to. And you'll see these used only on multi-zone systems where you've got these 2 for each of the indoor units. So each indoor unit, A, B, C, D, and E, they have their own respective ones for both the suction line and for the liquid line.
Darren, one question that just came in from Bob O'Brien. We appreciate you hanging out with us. Can you diagnose these thermistors just by checking resistance? We kind of talked about by voltage because we know that we have an incoming 5-volt supply voltage and we have a variable 5-volt voltage coming out that we would compare towards the chart that is in our service manual. But what about just resistance alone?
The answer simply is one word.
Yes.
So you just need the information on those thermistors to know what values they're supposed to be at. One of the things that we have that's free to all the contractors out there is our mobile technician app.
Oh, okay.
So if you went on to like the Google store or the Apple store, you could download our mobile technician app.
Okay. So is that Fujitsu mobile technician app?
Yep, it's
Awesome.
free. All right. So we got a 3-way thermistor. This one is monitoring the liquid line. So again, it's when you're looking at these, it's like, well, which one's which? Well, you could trace these out to see which one's going to which line. Again, if you were to have just one of these go bad, you get the whole harness.
Yeah, makes sense.
You're looking at 4 of them here. So that's what the 3-way valve would look like on the thermistors. So you have 2 suction line thermistors and you have 2 liquids. All right, let's look at a little bit on the indoor. So these are the indoor thermistors, and I'm sure this varies from manufacturer to manufacturer. But on the right-hand side, you can't pull that off. If you give that a yank, you're going to end up with a whole new board and everything because this one's actually soldered to the board. This thermistor.
Oh, okay.
The one on the left is removable, and all you do on that is you just push in on the side of the clip. While you're holding it in, you just lift it straight towards you, and it will just come right off. So some are soldered, but the majority are more of a removable style, which I like. All right, now we're still back at the indoor unit. This is the so we've got an indoor pipe thermistor. That one's looking at the refrigerant flow, and again, it's setting back a return voltage. You can see how it slides down into that little bitty well right there. So it's looking at what's going on with the temperature. Now, the system could start doing some interesting things depending on whether that coil is clean. So if that coil inside gets dirty, you can see that we could have some capacity dropping because the system's trying to slow down because the line's getting too cold. So it's interesting how that is working in relation to superheat and subcooling. So our system is looking to hit both a superheat and subcool target, which, by the way, you cannot set the superheater or subcool. That's all handled internally by the system, and the system is monitoring that continuously. So there are no charts for that. case you wondered.
Yeah, I have noticed because it gives a range. Said your superheat subcooling range would be in this.
Right. So let's talk about how the components work together.
Yeah, definitely.
A lot of guys have probably seen some things like this before, but we have the AC coming in. We go through the diode bridge, and you have what we call half-wave ripples, and then we go through a bank of capacitors, and we're trying to clean up that DC power. And so that's just the basics of how we make it through there to get that final good clean DC.
So we come in as typically, if we're talking a residential application, whether it's 120 or 208, 230, 240 volt, we have single phase AC coming in, going through our bridge rectification circuit, turning it into a DC supply voltage right at our capacitor banks. I have noticed on a lot of our control boards, they have test terminals on the boards for verifying that we are storing DC voltage. Is that true on most?
Yeah.
Okay.
All right. So this is the what we call the inverter pulse amplitude modulation, and this is a little idea of how it all works. So as you're looking at components, we're going through the diode bridge, which you see there in that little green.
Right.
We go through the rectification of that. We go through the capacitors. From the capacitor, we go through the active filter module. We're going through a main circuit board. The main circuit board is going to feed the IPM, which is what controls the speed of the compressor. And then the main circuit control board is also getting information from thermistors, and it's also sending information out to the fan motor and the four-way valve. So that's just kind of a quick look at how that's happening, component-wise from.
Yeah, who's doing what?
Yeah.
Very
All right.
nice.
So if you're looking at the top if you take the top off the equipment,
All right.
and this is just a nice little picture that shows where the power supply is on the right. You can see that you've got your diode bridge. The diode bridge then feeds over to the active filter module. The active filter module sends information back over to the inverter power module, which is, you can see the arrows pointing to the area where that's what.
That's the piece of the board.
That's the piece of the board that takes care of the speed of the compressor and how it's going to modulate. So I can tell by looking at this one, just because it's all one big board there in the center,
Mm-hmm.
I know that is a multi-zone system.
And how is that?
Because if it was a single zone, it would have been that little smaller square board that we showed you earlier.
Ah, okay.
So just, if you just walked me up to it and didn't let me look at a model number, I could just look at that board and know you got one of our multi-zones, whether it's a dual or a tri.
Mm-hmm.
So there's some additional ways that this works. So let's take you through this. We've got the power filter board. We went through the active filter module. We went into the IPM. So the DC voltage is provided to the active filter module. The active filter module is going to provide the proper DC voltage back to this IPM. And then the IPM is going to provide the DC voltage and pulses. And this is what creates that three-phase of stimulated AC power to the compressor windings.
Sure. And that's a question that gets brought up quite often. Is it AC or DC that is feeding our compressor motor?
Yeah. So whenever you take a reading and you go into actual literature, if it tells you to, check from here to here, it'll tell you what that voltage,
what it's going to look like.
That's right. So the manuals that you get, whether it be a service manual, service instructions, regardless of the inverter that's out there, they'll actually tell you what your voltage reading should be, and you should see it fluctuate.
Okay.
If you just get a number that doesn't fluctuate, if it's just one number and it won't move, then you've got a problem with the board.
Oh,
so you should see the voltage varying on that compressor.
Okay.
Now, let's take a look at how the voltage moves from the outdoor unit to the indoor unit.
Yeah.
So here we have on lines 1 and 2, we have the 208, 230 volt. And that's where your power is going to go to the indoor unit. Now, the indoor unit is going to, at its board, take that information and then tell that motor what it needs to do on speed. So we just have to get it to power the indoor unit. So it's not like the indoor unit has to have its own separate breaker or anything like this. Many splits will use the outdoor unit to power the indoor units. In this case, I know this is a 5-zone system. It has the capability of connecting 5 units. It happens to have 2 connected to it right now on unit A and unit B. All right, so if I go right here, you should see a fluctuating AC voltage on 2 and 3. This is the communication wires that information is being handled both inside and outside. So they're both talking to each other. It's also critical to remember that if you don't connect this dedicated green ground wire, you could have some intermittent problems with the system, sometimes working, sometimes not. So one of the things we always look at is if someone says, hey, this thing's sometimes it works and then it works for a while and then it doesn't. The first thing our tech guys will ask you is how many wires are connected to the indoor unit.
Yeah.
If it was only 3, well, don't you have dedicated green ground wire? No. The first thing they would have to do is make sure they've got that, because we're trying to isolate the AC from the DC on wire number 2 by having that dedicated ground.
A lot of people don't understand what is happening there on that number 2 wire. That is a shared, somewhat common between our AC and our DC voltages.
Yeah, a lot of people don't understand how they both can exist on the same wire.
Exactly.
And I always say, well, do you ride a motorcycle? Yeah. Well, do you have an RV? Yeah. Do
you ride them on the same road?
You have a semi? Well, they all travel on the same highway, right? Yeah. And yeah, they can share the same wire.
Absolutely.
So we have a forward serial signal that has to come, and in order for that indoor unit to talk back to the outdoor unit, that's going to send a forward signal from inside to the outside. So it looks like that. And so it's constantly giving information to the outdoor unit. And then we have a reverse signal. And then we have the outdoor unit saying, okay, I got you. And so you'll have a reverse signal going back on number 3, back to the indoor. So they're really talking really heavy on wire number 3.
Okay. But I would read that as a AC voltage. So if I put my meter on volts AC, I'm going to see a fluctuating voltage between number 2 and number 3.
Yeah, and it'll be jumping around like crazy.
Okay, so some meters may not even be fast enough to pick it up very easily.
It'll pick it up. It's whether your eyes can focus
on notice it, right?
But the way I always do that, I just look at the meter, and my brain says, don't look at the whole range. Look for the lowest number you see first.
There you go.
So it's sitting there jumping around, and if I see 40, 70, 60, I'm looking for the lowest number, and I'll write that down. Then I'm like, okay, now let me look for the biggest number, and I'll see it jumping around, and I look for the biggest number. And as long as I'm within the range, then I'm good. If I get outside of that range, then I'm going to probably end up looking at replacing the board.
And what would that range be?
It could vary. It could be anywhere from maybe 60 to 130, or it might be 30 to 160, or it depends on the model.
Depends on the system.
Yeah, but your eyes pretty much have to make sure it stays within that range.
Okay.
So just how good are your eyes? All right, so on a multi-zone, just a quick note here. A lot of times when you're looking at multi-zone systems, you do have to put in a minimum of a certain amount of units
on our capacity.
On our AOU 45, you have to have at least 2 indoor units.
Okay.
You're always going to connect from the A circuit up, because the A is the bigger set of lines. The A is always for the largest indoor head that you've got, and then you work your way up this ladder with the smaller units as you move up. And you can also put in a capacity range on this particular model, between as low as 34K or as much as 54K of indoor head connectability.
So 100 and
the system will run
30%.
Yeah, so if you make a mistake and you put too much in, or less than what you see on the screen, you're going to get an error on startup, and it'll be like you've got a capacity error.
Oh, okay.
And right then, whoops, maybe we.
Oh, I got a 42 instead of a 24.
Well, in this case, you might have installed 32K worth of indoor heads, and you don't have enough, or maybe you installed 56 and you put too much in. Well, all you'd have to do in a case like that is take one of the indoor heads and go get one a little bit smaller,
proper size,
and try to get it within the range.
Okay.
It's pretty rare to see that happen. So if you did take this 45 model of ours, this is how it would look if you connected up different styles of indoor units to the outdoor unit with the power wires.
And very important to make sure that our refrigerant line sets are matched to the control wires for each particular circuit. Seen it way too many times out in the field where we get our lines crossed, and so we may be trying to operate a unit and sending refrigerant to another one that has had no signal to actually turn on.
Yeah, there's nothing like having refrigerant flowing to an indoor unit that the fan's not even calling. Nothing's calling. It's just getting refrigerant.
Yeah, exactly.
So yeah, that can happen if you don't do your install and label them where you're running your line sets to. And
That's
your
right.
All right, so let's look at the system overall system operation. And when you start getting into multi-zones, they're going to manage capacity demands differently with each indoor unit depending on where they're at. So they're all the indoor units are communicating their capacity to the outdoor unit. The outdoor unit, again, there's an EEV for each of the indoor units. So depending on whether the family room or your office downstairs or whatever it needs, like in my office here at the house downstairs, I've got multiple computers, multiple monitors. You've seen those earlier when we were talking.
Right.
This little room gets warm. Well,
a lot of heat.
Yeah. So in my case, I'm going to end up putting a little 9K mini split into this office.
Yeah.
So I can control it. But in a standard system, you're only going to get so much air out of a vent. Well, that's not enough. Well, that's the beauty of if I had a multi-zone on this house, this office could have its own indoor head working with that multi-zone, and I could get, the amount of cooling I need depending upon how much heat I'm generating in this room at the time.
Absolutely.
So this compressor and the outdoor fan motor have to be able to modulate to maintain the correct capacity. So depending upon what's going on with the different zones is going to depend upon what speed the compressor is going to have to run at. Now, just because the compressor and the fan outside has to ramp up because you've got 2 or 3 indoor heads now calling,
right,
it's not a problem, because the EEV and the outdoor unit is going to tell the indoor unit, well, you need to speed up your indoor fan motor because you're monitoring your own temperature there, and I'm sending you a certain amount of refrigerant on this EEV to you. Well, that indoor head doesn't care what's going on with any other indoor
with
head.
The rest, yeah.
The rest of them. It just knows what it needs. So the system is getting all this information from all these thermistors, from all these indoor units. And it's looking at what's happening with all these indoor units collectively. And it says, I now have a third one that kicked in. So I need even more refrigerant so I can send some additional refrigerant to that indoor unit. So I've got to open up that EEV. Well, I need to speed my compressor up to this level and my outdoor fan to that level. And that's the beauty of multi-zone. And it's one of the most perfect zoning systems you'll ever install.
I agree. So I actually have a 4-port that I use here for my garage, my studio, and my workshop. So I have one head. I have a 24,000 in the 2-car garage. I have a 12,000 in the studio, and I have a 12,000 in the wood shop. So that depending on the area that I'm working on, I can control just that specific place. And I absolutely love it.
All you got to worry about the wood shop is how clean is your air filter.
Yeah, it definitely gets cleaned more than the rest.
All right, so let's look at the flow. We're getting towards the end of our presentation, but I wanted to touch some on how the cooling cycle works on the refrigerant flow. I'm not going to show the heating side, but so okay. Now just for everyone that's watching, if you look at the remote, the wireless remote on the right bottom corner, I'm going to click, and this is going to represent that zone. Now we have 3 zones here. That's zone A, the one in the middle, zone B, and the one C. So this is how the system is going to operate. So one of the mini split indoor units tells the system to start up. So my compressor starts up. I go through the outdoor heat exchanger, and now I'm going to send some subcooled liquid to all the EEVs in the outdoor unit.
At the outdoor, okay.
Now, the one inside on unit number A called for it. So now I've got refrigerant going through it. It's going back through the 4-way outside and back to the compressor. Now, this system's just going to keep running. Let's say the other 2 are just fine. They don't need anything. This system could run, satisfy zone A, you see right here, and then it could cycle right back down and be just fine. But now the summertime gets even warmer. Now a second zone calls. The first zone is calling. Now the second indoor head calls. And so the EV just opens up. The indoor fan starts to turn. Now I've got two of my indoor units running. Still have one that's not. Well, finally,
Right.
let's say it's really super hot out and everything needs to be running. So then the outdoor EEV opens up and my indoor unit now becomes active. And you can tell as I bring each one of these on, you know that that compressor and that outdoor fan motor is going to have to speed up to get rid
Right.
of it.
So it's good. The outdoor unit is going to change its capacity based on the load coming back from the indoor units.
Yes. And that is remarkable brains for technology.
Yeah, there's a lot going on, but when we understand what everyone is doing in association with everyone else, it paints a bigger picture of how they actually function. Because too many technicians will walk up to and go, I was taught this, and what I'm seeing is not that. So I'm not comfortable working on this piece of equipment. Well, it all comes down to education and properly understanding sequence of operation and the way that our components work in conjunction with each other.
So let's talk about the heating capacity. And this is interesting because when you compare it, we are going to do a quick comparison against a traditional heat pump.
Okay.
But if you notice that now keep in mind, this is a two ton model.
Right.
At 47 degrees, it is providing more heat than the size of the unit itself.
Right.
At 5 degrees, it's
Still producing a lot.
a lot. All right, so let's take and let's do a comparison now against a traditional. The traditionals on the left, the mini splits on the right. This happens to be one of our 2-ton traditionals on the left and our 2-ton mini split. When you look at 17 degrees outside, we are providing 10,000 more BTUs of heat with our mini split than we are our traditional heat pump.
Yeah, it's pretty significant.
That's a lot. Now, when you get to 47, okay, they're a little bit closer. You know, we have more heat in the atmosphere, but
Sure.
you start getting into colder outdoor temperatures. That's what separates heat pumps on the mini split side from traditional.
Yeah.
We can generate so much more heat that it's possible that we don't even need auxiliary heat backup.
Yeah, exactly. Especially when we look at the COP performance of that at 5 degrees, we're still 80% more efficient than an electric heat. So electric heat running a 1.0 COP, 1 watt in, 1 watt out, we're running 1.8 watts of heat output for every watt of electrical coming in. So significantly more efficient than electric resistance heating.
Yeah, so if we're going to compare the two now on the KW side, the mini split on the side, it's giving us 10,000 more BTUs, and we're using only 3.3 kW, whereas
Wow.
the traditional is taking more power at 3.7
And producing less heat.
and producing less heat. So that's why there's such a big advantage to mini splits. That's why they're becoming so popular.
Yeah.
That's why more contractors are looking to put those in rather than traditional systems.
Yep.
So again, when we get into heating, there's partial load operation. We talked a little bit about the speed of the compressor. This one is, it's got a range of 24 to 110 on a 18 and 24, and a 20 to 95 on the RPS on a 3-ton. So again, that it's going to have an operation frequency range as well. And it's also looking at, we talk about reducing overcycling. This is big utility companies, because they're like, well, how do you keep from, overcooling a space if you're designing this based upon a winter temperature that's really brutal?
Right.
Well, that's because the system has a wider range of where it can operate.
Operating capability.
Right.
Yeah.
So it depends on whatever zone we're in here, whatever this outdoor temperature is at, is going to determine what range we're going to run in, what speed of the compressor and what speed of the fan. So when we start looking at these frequency ranges, you're looking at them here 1 through 6 in this case. You can see that the arrow, as you go up to 40 RPS, that's where this one's going to start out.
Right.
It runs for a certain amount of seconds. Then it will ramp up the RPS gradually.
Okay.
Well, if you can satisfy the space in 200 seconds, you don't need to go to 110 or higher.
Sure.
You're already on a mild day. You don't need to go to full. It's nice to have that fast Corvette, but you're only going 1 block down the road. Why do you need to go spin the wheels? Well, that's why we don't need to modulate way up to high on a mild day. We don't need to go that fast. So if the system So this system may never reach the higher stages if the room temperature has been achieved. That's the beauty of it on mild days. Now, if it's really super hot outside, you're still going to ramp up through the sequence.
Right.
But again, if you have a day where it rains, well, guess what? The temperatures are going to drop, and you're going to be modulating even lower. And the interesting thing about this is, let's say that a contractor buys a 25 SEER mini split system. Can you imagine what the SEER rating would be if you're modulating?
Yeah, at reduced capacities.
Reduced, you might be what, 40, 50, maybe 60.
Exactly.
Well, you don't know, but you just know you are sipping on energy. It's kind of like if you had an expensive bottle of wine and you spend $100 for the bottle, you're probably not going to gulp it down.
Right.
You're going to sip on that bottle. Now the
right.
Bottle, you got to
reduce capacity.
Yeah, you go and say, "Well, give me another glass of that." Right.
Right.
It costs me that much, but so that's how these frequencies work. They vary again from model to model. The one at the top shows that it's got a different second amount of range.
Different timing
wise than maybe the 3 tons. So again, depending on the model, it's going to depend upon when it's going to speed up and when it's going to slow down. So if you want to see how the partial heating capacity works, the 4 major bullet points that talk about this and how the compressor is going to ramp up from 40 RPS and operate for 2 minutes. The compressor will either increase or decrease whether it needs more capacity. If it does, it's going to move up to the next RPS that's programmed to run at. And so you see that there's a thought process from engineering on how we're going to run this for a certain length of time. This will vary from manufacturer to manufacturer.
Yeah, absolutely.
But everybody's doing something similar, and at what point they're going to decide they're going to ramp to a certain speed.
Right.
And so when we're talking about partial load, you can see from this example that this little 9,000 indoor wall mount unit has a heating range of between 3,100 to 22,000.
Wow.
So if it's really warm outside, if it's 59 degrees outside, you could possibly get up to as much as 22,000 out of it.
Wow, that's pretty crazy.
You might get more.
Yeah.
But this just gives you an idea of the kind of ranges that these can modulate in. And again, it depends upon what the differential between set point and the indoor temperature and the outdoor temperature is. So it's looking at all those things to determine where it's going to be at in that range.
Wow. Okay. Lots and lots and lots of great information. We still have quite a few people out there. Anyone have any questions or comments at this point? Definitely appreciate everybody joining in today.
Are you ready to buy or install a mini split?
Yes, absolutely. I have both systems. So I've got a traditional, purchased a new house about 3 years ago. The home itself was conditioned with a 95% gas furnace and a high efficiency air conditioner, right? It says high efficiency on it, so it's got to be high efficiency, right? 14 SEER. Yeah. And then I have my nice 21.5 SEER that I utilize out here. And I will tell you, I absolutely love my multi-zone inverter systems. So my next opportunity will be to upgrade the house with a inverter-driven heat pump. Now, I still like having my gas furnace. I like having dual fuel operation in the home. So it will definitely be a modulating gas furnace with a inverter hybrid system. But I adore what has happened with inverter technology. And just from the installation, commissioning, and troubleshooting aspect, it is an evolution to our industry.
Yes, and one of the interesting things about the inverters, if you've ever had one, and I didn't truly appreciate until I got mine, is that you set it and you leave it alone.
That's right.
Because when it modulates, it's going slower. So like right now in my office right now, downstairs, when the system runs slow, I'm putting air into the room at a slower pace.
Yes.
So I'm not like overshooting and putting in too much or not enough. And I've noticed that my temperature is more even and more comfortable throughout the house.
Yep.
Rather than just a full blast and I shut off.
Yeah.
So if you want the maximum in comfort and zoning, it is the way to go.
No, I completely believe that. And as we start talking about new refrigerants coming out, we're even going to have refrigerants that have a little bit more heating capability than the R410A that we're already accustomed to. So the technology is just continuing to advance, which is why it's critical to become better educated on these products. And that's why we're all here today, just to get a little bit smarter on what's happening in our industry.
That's what it's all about.
All right. Well, I don't see any other questions coming through. If someone is needing to learn more about Fujitsu, what's the plan to learn more about Fujitsu products?
Well, if you're a contractor, you can always go to our website at www.fujitsugeneral.com. Or if you're a homeowner, you want to look at that, you can look at all of the different things we have there for homeowners to browse. If you're a contractor, you can always contact one of your distributors and talk to them more about the product.
Okay, fantastic. Well, Darren Kramer from Fujitsu, we appreciate your time so much. We hope this was an opportunity for everyone to learn a little bit more about the world around us. And we will see you all next week on Did You Know? The ESCO HVAC Show. Are you looking for a new adventure in audio education? Then look no further than the new opportunity from the ESCO Institute. Did you know? The ESCO HVAC Podcast. Join us from your favorite podcast network as we share stories and lessons from industry professionals like you. Find all of the ESCO resources at escogroup.org.